Speaker of this afternoon's session is Mike Cates.
Thank you very much. I'm going to speak about active liquid crystals and will relate them to a biophysical topic to do with cellular locomotion. I'm aware that this is a liquid crystals meeting, not a biophysics meeting, so hopefully you'll recognize that mostly the talk is about liquid crystals with a twist, the twist being an active stress which arises from biological time irreversibility, if you like. So I'll say a little bit about what's understood about how cells move, focusing on locomotion in higher organisms, eukaryotes, that's us. In particular, there's a well understood mechanism, cellular propulsion involving polymerization of actin. But what I really want to do is focus on this alternative route, which is actually quite a lot simpler, which is the idea that you can basically put a blob of an active liquid crystal into a droplet and it will swim. That's what I hope to persuade you of. And there may be some relation between this very simple mechanism and what's actually happening in some types of cellular locomotion in places like your body. So let me very briefly fill you in on how cells move around. So there's a lot of work on the motion of bacteria, which I won't be talking about today, but something that we've been interested in as well. So you have objects which are micron sort of size, a bit bigger for cells of higher organisms, in some kind of viscous medium, negligible inertia. So to move, you have to break time reversal symmetry. And the main way this is done by single-celled organisms, such as bacteria, is to have some kind of outboard motor consisting of a propeller, basically, or you can swim by waving these arms around if you're an alga. So that's for single-celled organisms, but if you look at the cells in your body or in more complicated organisms, they don't move like that. They don't have outboard motors. They do something involving modulating their own shape, which allows them to make progress either through a tissue or moving in a fluid or crawling on a surface. So to talk about this process, I'm going to have to tell you a little bit about the cytoskeleton of eukaryotic cells, and I'll tell you about this crawling mechanism, and then I'll turn to the liquid crystal story. So first thing is to just let you know why cells need to move. Well, if you are an embryo or a young person, obviously your body is changing shape and cells are moving around. But even just maintaining healthy adult tissues, there are also cells moving in many cases. Certainly if you cut yourself or if you have to conquer some infection, your cells have to move to heal wounds and to track down invading bacteria or whatever. So those are good ways in which cells move around. A nasty way is if you have a tumor and it starts to metastasize, or whatever the word is, so the cells can break off the tumor and start spreading around. This is not a passive process. They actually move in a systematic way through tissues. So there's lots of experimental biological work on this. A lot of it, though, in vitro, so in your test tube, a lot of it is done with cells which are stuck to a wall. And cells can move near a wall by a kind of crawling motion, which I'll describe in a minute. So most of the experimental work is limited to some fairly specific cell types, or things called cell extracts here, or which are kind of reconstituted bags of biopolymer and motor type material, and there are other cells where you can just chop off a piece of the cell and it will also move. So let me show you a couple of movies. On the left is a keratocyte. This is something you get by scraping the skin off of fish. So this is fairly typical. This piece at the front is called the lamellipodium. So it looks like a fried egg. It's got this big piece out front, which is where the action is in terms of the motion. The nucleus lives in here. and on the right is a white blood cell. This is I think this movie dates from the 1950s. You can find it everywhere on the web now. This blood cell is chasing a bacterium here. So it's moving by this kind of amoeboid motion in which it's changing its shape in order to get along. So if you want to move, then you need an energy supply. So this is supplied by a molecule called ATP, as you may know. You also need something which is a kind of reconfigurable skeleton called the cytoskeleton, which, as we'll see later on, is often modeled by, from a physics perspective, as a kind of liquid crystal. And I'll show you it has a polarization, it has orientational order, it has various things that you'd expect a liquid crystal to have. So inside the cytoskeleton you have filaments, which are long rod-like molecules which can give you the orientational order. The filaments actually have a directionality, which I'll explain a bit more in a minute. So each filament has a front and a back. And on these filaments, you have myosin motors, which are consuming ATP. And these basically hook onto two filaments and crawl. And they do that in such a way to create what is called a contractile stress. In other words, these two filaments here are moving together, and the surrounding fluid develops a flow with the symmetry that is shown there, or cartoon style here. So this is pulling fluid in along an axis and shooting it out around an equator. The opposite of that, where you pull in around a disk and shoot out along an axis, is called extensile, but that's different from what I'm going to talk about. So yes, this is just a little toy movie of what that motor is doing. So that's the ATP coming in, etc. So you don't need to know about the biochemistry here. What you need to know is that in the cytoskeleton there are filaments with polarity and an entity which is capable of producing a stress that violates time reversal symmetry. So but there's something else which also is happening inside the cytoskeleton, which is this reversible. It's a polymerization process. So if you look at these filaments, what you actually see is something like this picture here. So they're polymerizing from one end and evaporating off the other. So this gives you a tendency of each filament to progress along its own polarization vector. They're rather confusingly drawn like this, with the plus end, which looks like it ought to be really the minus end. But the monomers of this protein monomers land at this end and fall off at the other, and the polarization vector is defined to point this way, which means that these filaments tend to make progress along their own vector. So to understand in the simplest way how cells might move, what you need is this stuff and put it in a bag. That's a cell. So you might put it inside a membrane, or even simpler from the point of view of mathematical modeling, you might just confine it into a fluid droplet and say this is in some other fluid as the surroundings, so that it just is a confined space in which this stuff can live and do its thing. You may also need frictional contact with the exterior world, and if you're going to do this crawling mechanism, which I'll say a little bit more about in a minute, there's something called focal adhesions, which actually couples these actin filaments through the cell membrane to the outside world and allows you to grab hold of your environment. But the thing which is seemingly inessential is real biochemistry regulation. So if you're a biologist and you're shown all this stuff, the biology worldview is you have some extremely complicated biochemical network which you write down and you say this is the reason you move. If you're a physicist, you might think that, well, you should be looking for mechanisms which are intrinsically allow motion out of very simple ingredients, and then the biochemistry is really the steering wheel. It's really the control mechanism for this inherent process of spontaneous motion. So it seems that you don't need the biochemical network, and the way you show that is you just get myosin, actin, put it in a bag, and it will move. as long as there's an ATP supply. So you have to feed it, but you don't need to have a complicated control structure telling it that it ought to be moving around. It will do so spontaneously. Likewise, if you go to that crawling thing I showed you with the lamellipodium, you can come with a laser, slice off the lamellipodium, which doesn't have the regulatory networks and doesn't have any genetic material in it, and it will continue to move. Okay, so this is the top view. This is the lamellipodium up here. You've got these polar actin filaments here, and as I've drawn here, the polarization is pointing forward. And there are some filaments pointing the wrong way, but it's nonetheless has a net polarization. So that's something like a liquid crystal, polarization field P. And I mentioned these focal adhesion complexes, which are proteins which connect to the filaments and stick through the cell membrane here onto, if you're crawling along a glass wall, they stick to the wall. So this process is a kind of crawling. It's often called, well, the polymerization process is called treadmilling. And by polymerizing at the front and losing monomers off the back, you can imagine that this whole thing will move forward basically like a tank. And then the focal adhesions give you a no-slip boundary condition, which is what you need here. So that's the crawling mechanism, which, as I say, is reasonably well understood. But it needs a wall. Okay, so what I want to do then is tell you about this alternative route to cellular locomotion, which is simpler and is best understood from a liquid crystal perspective. So I'm going to talk about a droplet of a polar liquid crystal with contractile active stress, and I'll say mathematically what we do to describe that. So just to motivate that a little bit more, the question that we were trying to understand is, if I have a cell with the cytoskeleton and the polymerization and bits and pieces that I've described, do we need this tank treading mechanism? Is the polymerization or the motion of a filament along its own vector, is that the key thing as widely assumed, or is there a simpler thing that can happen that can also allow you to move? Well, most of the literature does appeal to this polymerization process as the source of cellular locomotion. There's a bit of evidence from a group in Paris and Rhoda Hawkins, who's now in Sheffield, a particular relation to cancer cells in three-dimensional tissues, which suggests differently. So I'll come back to that at the very end. So if you can move without this tank treading mechanism, how do you do it? It has to be some kind of swimming mechanism rather than a crawling mechanism. When might that help you, and what's the simplest model? So I've already given some indication of what this simple model will look like. So this is what we think is the simplest model: a bag of active matter. So the cytoskeleton has these fibers in it, and it has the motors, and I'm just going to describe that using the language of liquid crystals. So I have an orientational mass distribution, things that are pointing in direction U, so that's these actin fibers. So there's a concentration field, first moment of that. Polarization, is the zero. Polarization is the first vector moment of that, divided by C. So this is how you would describe the statistics of vector particles. You could, for most of what I'm going to say, you could replace that by an even more standard description in terms of a pneumatic. In other words, if you don't have this polymerization effect, which moves you along your own arrow, then these fibers here you might as well think would be headless fibers, in which case you talk about a Q tensor, as you're all used to. There is a difference, of course, as to what kind of topological defects you can support, and the experimental evidence is that you actually need a vector field, not a Q tensor for actomycin. But unless you have topological defects in your moving blob, you needn't worry about this. So there's a parallel to everything I'm going to say in terms of P, which can be written in terms of Q. And the physics that I'll describe has an almost exact counterpart. Anyway, I'm going to stick with P. And the next thing we want to do is confine this. So I'm going to have some of this stuff and confine it. So the biologically honest way to do that would be with a membrane, but I'm going to do something simpler, which is to just put it inside a fluid droplet. So I imagine that I've got a binary fluid, so a fluid with two components which are immiscible. So that will create, with that idea, I can write down a free energy. Here it is. C is the concentration field. This is just a standard double-weld free energy with a square gradient piece. So this will create states of, just by convention here, 0 and 1 as my concentration of the actomycin. These states have equal mass density, so it's not that I'm doing this in a vacuum. I'm just saying I've got fluid A in fluid B, and fluid A is the droplet of active matter, and B is the surrounding Newtonian fluid. So, as ever, the parameters here, coefficients for the bulk part and the square gradient part, fix you an interfacial tension. So, this on its own, it's very easy to make a droplet. It has some interfacial tension inside it. The concentration of actomycin is about 1, and outside it, it's about 0. So that's just a way of making the this material all be in one place. And I've told you it's polar. So again, this should not look too unfamiliar to this audience. So this is again a quartic free energy here, designed to give you a spontaneous symmetry breaking in states of finite polarization, and the coefficients here are scaled to give you an equilibrium magnitude for the polarization vector of unity. That's just a choice of units. And another simplification, which again many of you will be familiar with, at least in the context of Q-tensor type description, is that in writing the square gradient terms for P, we have a single elastic constant here instead of the three independent constants that you might introduce for splay, twist, and bend. So if I just have a uniform density of actomycin, its free energy is given by this, which says that it wants to be polar, and you have to pay a cost for bending the orientation, or splay, or twist. So these two things need to be coupled together, and if I introduce a simple term here, which is P squared times something proportional to C, all this does is it makes sure that I don't have a polarization field outside the droplet. So I'm making a droplet, and this is just engineered to make sure that when the concentration is less than half, so that's the exterior, the equilibrium polarization is 0, and it's 1 inside. So to summarize that, this is the free energy functional as a function of the concentration and polarization of the active component. So there's your binary fluid term. Here's your polarization term. If I left something out, I've left out. Actually, I've organized the coefficients here so that that coupling term is now included. So what happens when you just look for a local minimum of this corresponding to a droplet state? You have a certain concentration slightly shifted by the coupling term. You have a uniform interior polarization, again slightly shifted by the coupling term. Exterior concentration about 0, no polarization outside. You may have noticed if you're eagle-eyed that I haven't included any anchoring terms here, so that the polarization of the actomycin in this bag doesn't care how it's oriented in relation to the surface. So this is an extremely simple thing, and there's all kinds of ways in which, especially on that last point, that I could improve it to have P pointing outwards at the surface or whatever. But for now, let's take that picture. So, so far, everything I've told you about might as well be dead. There's a concentration of stuff, and the stuff has a spontaneous polarization, but that's all. So we need some equations of motion, and when we write those down is when the fact that this is a living system will matter, but will matter only in a very simple way. So the protocol here, which is basically following a body of work started by Sriram Ramaswamy and Jacques Prost, is to say, well, write down the simplest thing you can, and if you want to describe a biologically active liquid crystal, add the simplest terms that you can add, which are present only in the biological case. Those terms are terms which violate detailed balance, which break time reversal symmetry in a way that an equilibrium system cannot do. And the existence of those terms depends on the fact that you're consuming ATP. You have a biochemical engine which is driving the system out of equilibrium the whole time. So let's see what we're going to get for the equations of motion. So here is the time evolution equation for the concentration field. So the idea is that this is just like you'd have in a binary fluid. So if I look at this dc by dt grad CV, that says that there can be a fluid velocity. This is the gradient of the chemical potential. So that's what you'd expect to see for a dead system, but in the case where you're alive, you have this strange and interesting term here, and that is called self-advection, and it's the first of the two terms that you need to add to reflect the unusual physics that's going on inside the cell and the breakdown of time reversal symmetry. So V is a fluid velocity, M is a mobility, so this is just standard binary fluid physics. So this W is basically telling you about this treadmilling effect. So what it says is that if each of these filaments basically acquires matter at one end and loses it from the other, if I look at this picture, then a short while later the liquid crystalline material will have moved to occupy the black arrows rather than the blue ones, and that is mass transport. If you've got a net polarization, that's mass transport along the average polarization direction. So that's why it's called self-advection. So such a term you could not have in a system with detailed balance and time reversal symmetry. And you'll have spotted here that obviously there are monomers moving around which have to come off the back and arrive at the front. So this is already a coarse grain description dealing with the filaments but not the monomers, which don't have the polarization field attached to them. Yeah, so that's that movie again. So the self-advection is a way of representing this process, and is what you get if you represent this process by only thinking about the filament and not about the monomers. Okay, so now we need an equation of motion for the polarization field, and this is standard liquid crystal physics, so I hope I won't have to say much about it. You still have a self-advection term here, so this says that the p vector is the usual total derivative with self-advection. This could be a different W technically, but that's a detail I won't go into. And on the right you have some standard stuff which many of you will have seen before, involving the symmetric and antisymmetric parts of the velocity gradient tensor, which basically tell you how the molecules rotate in the presence of a velocity gradient. There's a molecular parameter here, xi, the flow alignment parameter. So you have advection, including this rotational piece of the advection, which with a parameter which tells you how strongly you rotate in the presence of a shear flow, and a local relaxation, which again is completely standard. This is the molecular field, and that's a molecular relaxation rate. So P is not conserved, but it can advect. And just to remind you about the flow alignment parameter, which again I expect many of you know about. So this parameter is positive for rods, negative for disks. If I just take standard liquid crystals without any activity, there's a regime in which the order parameter is unstable under flow. We choose the flow aligning regime, which has this parameter greater than 1 to make sure that if we see instabilities, we know that they're from the activity and not from the intrinsic liquid crystal dynamics if I put this in a shear flow. Any shear flows that the system will make will, however, be generated spontaneously. So that's standard, except for, again, the self-advection piece here. And the Navier-Stokes equation. So this is telling us about momentum transport. So I have my vector field P describing the orientation of the actin fibers. I have their concentration, and I have the Navier-Stokes equation in which there is a stress term. So, as ever, the pressure field is found from the incompressibility of the fluid flow. And there's one thing before I talk about the stress, there's one extra thing you can do, which is just convenient for some kinds of numerical simulation, is to add an explicit drag term here. This is a Darcy-like term. That's just a trick. What it means is that if you want to do this, if you want to simulate in 2 dimensions this system of a thin sheet of active material crawling against a wall, then the frictional drag against the wall can be represented just by a term linear in V here. But you can also, when you code this thing up, you can also do full 3D simulations of things, droplets moving against a wall. So that's just a little shortcut which I will use very briefly later on. Okay, so the important thing is then the stresses here. So again, most of these, I mean, I usually have to apologize about how horrible and intimidating these things are, but hopefully to this audience they're not too bad, because most of them are completely standard. So all of this stuff, so there's the viscous stress, here's the thermodynamic or the elastic stress involving the molecular field and the polarization. Again, you can write all of this out again in Q-tensor language if you wish to, but this is what it looks like for P. So that's the standard elastic stress with including the single elastic constant terms here. And along very similar lines to that, but possibly less familiar to this audience, is the same thing, which is the thermodynamic stress, which comes from the fact that I've got interfaces. So this is just the same construction, basically dealing with the part of the free energy which is a functional of the concentration field rather than the polarization. So this stress here arises, it gives you the Laplace pressure from curved interfaces with surface tension sigma on them. Okay, so those are all passive and they're all standard. And the only extra thing, apart from the self-advection, which I already mentioned, which comes from treadmilling, the only extra stress here is the stress from the motors crawling along the fibers, which tends to pull pairs of fibers towards one another. That's giving you, with a positive coefficient here, it's giving you something proportional to concentration, but the stress is basically the bivector of P with itself. So that's what you have. And that's the origin of it, as I said previously. So the contractile stress is the simplest thing that you can add to a liquid crystal, which violates time reversal symmetry in steady state. It violates detailed balance and is the basis of the active liquid crystal story. And the only thing we have as well as that here is the treadmilling. Okay, so let me say something then about how a droplet made of this active liquid crystal might move. To do that, it has to break symmetry, and I will explain that story next. So, okay, so as apologies as usual for the fact that liquid crystals have complicated equations of motion. The only thing that you need to notice about this is, okay, so I've got the self-advection terms here, and I'm going to be interested in the case where the cells are not doing this, their self-propulsion is not dependent on this polymerization piece. So what I'm going to do is set W to 0. So then I've got completely standard liquid crystal theory, admittedly with the concentration field, except for this. So I have a completely time reversible standard system and an active stress that looks like PP. And what that means is that in the absence of the self-advection, so without this polymerization process, I just have motors walking on filaments. That's my only active physics. There's a global symmetry here. If I, at fixed hydrodynamic velocity field and fixed concentration, if I reverse the sign of P, then nothing changes at all. So implicitly in the literature on this kind of topic, there's an argument which sort of lurks and is not, I've not seen it explicitly laid out, but I think it's the reason that for quite a while people have thought that the self-advection is the key to locomotion. If I don't have any self-advection, so I don't have any treadmilling, then if what I've just told you is that if I have a certain droplet that's moving with speed v and it has a certain configuration of its polarization, concentration, change the sign of the actin orientation everywhere, then nothing changes. So v does not change sign. That's the important thing. And the crude argument, which is not quite right, is that p is the only vector from which you can make a velocity, and so without the w piece, so for w equals 0, cells are not going to move. That's the unfairly oversimplified to the point where you can see it's wrong synopsis of the literature on that. So that's not really true. I can make a vector out of p that doesn't change sign when p does, as long as I also throw in a grad, right? So grad pp in any combination, that's p squared. So if I change the sign of p, that vector doesn't change, but it's still a vector. So what that says is that I can have a motion that is controlled by p so long as p is not uniform. And so what I have to do is I have to start with my droplet in which I put this actin represented as an active liquid crystal, and somehow break the symmetry, not between p and minus p directly, but make sure that p is within the droplet is not of uniform orientation, and then the thing can move. Nonetheless, when I do that, again, if I think about this, any moving states of this active liquid crystal in a bag will come in pairs with the same velocity and with equal and opposite orientation fields in the two cases. Okay, so since this is a liquid crystal audience, I just want to get a little thing off my chest. Having a symmetry in the equations between plus p and minus p, and this symmetry breaking, is not a transition from a pneumatic to a polar liquid crystal. So I hope I don't need to explain that too much here. The point being that in a pneumatic, there's an intrinsic symmetry between the director and its negative, which is local. And a global symmetry and a local symmetry are not the same. So it's very important to realize that if you have actin with an alignment, even if it's not doing the this kind of self-propulsion thing along its own direction, that's still a polar liquid crystal. It has integer instead of half-integer defects, for example. Nonetheless, what I've told you can be completely repeated with Q instead of PP, and exactly the same thing is needed to swim in an active pneumatic droplet without, well, you can't have the self-advection in the pneumatic because you don't have a P, but you still need a spontaneous symmetry breaking to a state of distorted orientation, and then you can move. Okay, so let's put a little bit of physics on to that. So why do things swim if I do have this distortion? So here's the cartoon. So here is a droplet in which I've got some, in this case, splay. And this, it will turn out in a minute, will move to the right. Well, it is true that the velocity involves div p times p. That's the combination of grad and two p's that I mentioned before. The way to think about this is that we know what the active stress looks like. It's got pp. So that's, and this is the strength of the activity. That's telling you how much ATP is being used per second or whatever. So I take the divergence of pp, and it looks like div p times p. So you move along p with a rate which is proportional to div p. So this thing here is moving to the right because div p is positive. This thing, where I've reversed all of the actin filament directions, is also moving to the right for the reasons that I've said. So that's your plus minus p pair of symmetry broken states. But then the next question is, why does the symmetry break like that? And interestingly, it's exactly the same term. It is the active stress which does this. And in fact, it's quite well known in the literature on active liquid crystals dating back to early work by Sima and Ramaswamy, that the the presence of an active stress which looks like PP specifically tends to make you splay. And the reason for that is kind of roughly here. If you imagine having a set of aligned p vectors and you put a sort of a splay wave on there, and you look at the effective body force, which is the divergence of the active stress, this is pushing you up here and it's pushing you down there. So that, if I start with this flat, that modulation will grow. So in the bulk, in fact, a bulk homogeneous active liquid crystal, once you add the contractile stress term, is unstable precisely to this kind of distortion. So all we're getting is the same thing inside a droplet. And the only difference is that in the bulk, this happens infinitesimal activity, and in a droplet you need to exceed a threshold before it will happen, because you have to you have a kind of finite size effect to overcome. Okay, so the claim is then that to get a bag of actomyosin thought of as an active liquid crystal to move, I do not need the self-advection or the polymerization process which moves fibers along their own direction. What I do need is some splay, and then you can swim. So let me show you some simulations on this. So these simulations are done via a lattice-Boltzmann or hybrid lattice-Boltzmann method that I will extremely briefly outline. So lattice-Boltzmann is one of those kind of, I don't know what it is, it's like a cult. Either you're in on it and you know how it works, or you're not and you probably don't know want to know how it works. Anyway, it's a way of doing fluid mechanics on a lattice, but the important point here is basically a way of solving the Navier-Stokes equation as efficiently as anyone else can solve the Navier-Stokes equation. Works very well on big computers. The only thing to point out is that you need a version of the lattice-Boltzmann solver which can deal with an external force or external stress in the Navier-Stokes equation, and this is what we have. Now, there are ways of doing liquid crystals completely by lattice-Boltzmann, but recently we've, well, in the last 5 or 6 years, we've learned that the efficient way to do this is to use the lattice-Boltzmann to solve the Navier-Stokes bit of the equations of motion, and to use completely standard finite difference methods to solve the order parameter bits of the equations of motion. So the external force here, which is the divergence of the complete assembly of stresses, active and passive, that I've mentioned, this is computable if you know the order parameter. So that's what the external force is in the Navier-Stokes equation. And so what the Navier-Stokes equation does is it tells you the velocity, then you read out the velocity and you stick it into the kind of advective relaxation code that updates P, or advective diffusion that updates C. So that's why that's a good thing to do, but I won't say more about that. Okay, so I think I should probably go straight to some movies here. So this is a droplet of active polar liquid crystal in a fluid of the same density. This is in 2 dimensions for simplicity. I'll show you more complicated things in a minute. So the arrow is the polarization arrow. So it took a little moment there to break the symmetry, but it certainly managed. And that's just a tiny bit of numerical noise. You need to do that. So this thing has not got any of this self-advection. It's spontaneously splayed itself due to its own activity, and having done that, starts moving in the direction set by P times div P. And just to prove the point I was making earlier, this is actually the same, but with slightly different noise, and now it's broken the symmetry in the other way, and it is still got the arrows pointing to the right, but the splay is now telling it it's got to move to the left. So as a function of the activity, what you find is that you have a bifurcation, quite a crisp bifurcation at a certain level of this dimensionless number, which is telling you how much the system is violating detail balance by having this active stress. So below a threshold, the system fails to break symmetry, so it doesn't move. If I turn up the activity enough, it does break the symmetry and it starts to move, and as I mentioned before, it can be moving as a kind of a pair of complementary states. In 3 dimensions, basically the same thing happens. Slight twist here, and I'll show you movies in a minute. So this is the flow field, which it basically sets up a pair of or in 2D it's a pair of counter-rotating vortices internally in the fluid flow, which then infects the surrounding fluid, and that's how it moves along. This is a kind of a vortex ring. So these figures here are increasing the activity level. What you find is if you increase activity too much, instead of doing this, it kind of splays right round and has a defect in the middle, and then the symmetry is restored and it stops moving. So if you overdo it, it won't move anymore. So too much splay, and it reverts to the unbroken symmetry by having a defect instead. Here's a 3D movie. Same sort of thing. Just about to find its splayed configuration. Takes a bit longer, and off it goes. I hope that's visible. It's not very visible, perhaps. I have better pictures later on.
Can you say a word about momentum conservation?
Yeah, well, so so I mentioned this Darcy piece in the 2D simulations. We weren't using it there. It sets up a stress. So momentum, as you is sort of well known from the field of bacteria and so on, that if you're going to move by swimming, the way you do this is by exerting a forced dipole. So that if I draw a box around this thing, there is no net force on this box. All the forces are internal to the box. So momentum is conserved. What it's doing is it's just pushing one bit of fluid one way and another bit another, with equal and opposite impulses, essentially. All of the simulations are zero Reynolds number anyway, so they're all force balance in the Navier-Stokes equation. But there's no external force on this, and therefore the nature of its interaction with the surroundings is through a force dipole or quadrupolar field. Does that answer the question?
Well, sort of, except as it moves to one side, the surrounding fluid has to get away from in front.
Yeah, well, so this is done in periodic boundary conditions, and the surrounding fluid is flowing backwards further out.
Right.
That's what's going on. Yes, this is the higher, too much activity. So this one is going to start swimming, and now it's going to make a defect, and now it's found the defective state and it's stopped. Okay, so I'm going to skip that. I'll say just a little bit about motion at a wall. So you can do this with a wall. Here's a droplet moving at a wall. It's basically just like half of the previous movie. Slightly different final shape. So let me just finish with a couple of words about whether this may or may not have anything to do with actual cellular locomotion in you, for instance, or me. Okay, so I mentioned before that the viewpoint which is prevalent that you need to have the reversible polymerization to allow you to move is partly based on experiments where cells are, just for convenience, placed next to a glass wall. You can, of course, do experiments in 3 dimensions by labeling cells, looking at them in tissues or in fluid surroundings. And in that case, the focal adhesions, which are what allows the cell to anchor to a wall and crawl along, there isn't clear evidence that they are present in 3-dimensional tissues, certainly not in anything like the kind of density which the cell makes when you put it at a wall. And the evidence for the internal treadmilling with the polymerization process is also ambiguous. In particular, there are certain ways of switching that off, and at least some evidence that things still move. So this is unclear, I would say. What has become clear recently is that if you look at a tissue at a long time scale, a tissue is more like a viscous medium than a wall. In other words, you might think of a cell crawling through a fixed scaffolding of other cells in your tissue, in which case it might be using the mechanism it uses when it's crawling along a wall. But if you look at basically time-lapse movies of tissues, you find that all the cells, in certain types of tissue at least, are moving together. It's much more like a fluid. So just to finish with a movie or two here. This is, these are tumor cells. This is what you don't want to happen if you're unlucky enough to have a tumor. So I'm not answering this question, I'm posing it, particularly in the picture on the right. So the question is whether those cells are seeing their environment as basically a frictional goop and swimming through it, or whether they see that as a solid scaffold and are crawling along it. And I don't think we'll know this until people have got inside there with more refined type of labeling. So let me end there. Thank you for your attention.
Thank you very much. Antonio.
I was a bit puzzled by the reversal of sign of the velocity when you change the display, but not the direction of polarity, because naively I thought that polarity is related to the polarization of actin filaments, right? Plus n barbed ends and minus n pointed ends. And so is it, I mean, your mechanism would suggest that you could have motion with the filaments oriented with the plus n towards the trailing edge. Is that comment on this?
Yeah, well, what I'm saying is that if instead of using the polymerization as the method of moving, if you're moving by the polymerization, you can only move towards along P. If you're using instead the contractile stress essentially to make you swim, then you could swim equally well up or down P just by changing the sign of the splay. Because it's P times div P.
What gives the sign of the orientation of P then?
So, well, okay, so the way I'm thinking of it is you have this droplet, you have a polar phase in it. So that has its P lined in some direction, and then when it undergoes the splay transition, it can splay fan out, or it can fan in. And depending on which of those two things it does, it will either move along P or against P. And because polymerization is not involved, those are both equally fine. Does that answer your question?
Yeah. So, but then I need a microscopic interpretation for the polarization.
Yeah, well,
no. Based on
right. No, so this is what I was saying about the difference between this. I made this comment. The polarization of an actin filament is something that I can just look at the filament and tell you which is the front and which is the back. It has the monomers are oriented differently. It's like each monomer has a little arrow on it. And so that polarization defined that way exists whether or not it's doing the polymerization. That's important. It's not just when it turns on the polymerization that it becomes polar. It's always polar. And the way to think about that is that if you decided that it was not polar when it's not polymerizing, you switch off the polymerization, suddenly the defects meant to switch from half integer defects suddenly aren't allowed anymore. Well, they're there, right? If I turn off if I have half integer, sorry, it's the wrong way around. The structure of the defect is fixed by the symmetry of the molecules, and whether the thing is polymerizing or not, it's still polar, I insist, as long as there's a net orientation of the actin.
One more question.
So, you made the case here on this slide even that what matters is the gradient of the order parameter rather than the order parameter itself for determining the sign of a velocity. So I guess that leads me to speculate. Does the order parameter need to be an orientational order parameter at all? Or could it be some other kind of order parameter, say a scalar order parameter, like a composition gradient going across the droplet? Would something like that be able to
Yes, that's very interesting. I have certainly not thought about that from the point of view of a sort of continuum symmetry arguments. There certainly are ways of making things swim that don't involve any kind of liquid crystallinity. So there are in other bits of biology, there are things which swim by, excreting chemicals or whatever, like something like jet propulsion type thing. So I think in formal terms, you may well be right. I've not thought of that in this context, though. Yeah.
Okay, I think we better move on to the next one. Thanks again.